Well, hello there, Calculus 3 students. We are looking at section 15.3 today. We're looking to investigate and give some definitions for some conservative vector fields. We have definitions for both simple and closed curves. First, note that a simple closed curve is depicted here. This one, of course, is simple, meaning that it doesn't cross itself, so it's simple, but it is not closed. This one is closed. The ends are closed, but it crosses itself, therefore it's not simple. This one crosses itself, so it's not simple, and neither is it closed. Expanding that definition into connected and simply connected, we're just extending that, so this particular shape is both connected and simply connected, and what that means is there's no holes in our shape here. And this one is connected, but it is not simply connected because it does have a hole in it. This one is not connected, but it is simply connected because we don't have any holes in either of the shapes. This one is not connected because we have two separate shapes and it does have a hole. Therefore, it's not simply connected as well. We next have a definition for a conservative vector field, meaning that there must exist some scalar function phi on that region. Here is our test. We'll take the partial. Notice that f has a function. F is the I component, j and k component, and we must have that their partials are equal to each other. So let's test A. So the partial of f, that's the very first one with respect to y, is then, so we're going to take the partial of f with respect to y. So the partial of this with respect to y, the e to the x is like a constant. The derivative of cosine y is minus sine y. Partial of g with respect to x is then going to be, so I'm going to take the partial of this is going to be negative e to the x, and then the sine y is left as a constant. These two are equal. Since these two are equal, partial of f with respect to y equals the partial of g with respect to x. This implies that the conditions of theorem 15.3 are met and f is conservative. I'm going to play the same game with our b, this time in 3 space. So let's look at the partial of f with respect to y. So I'm going to look at this f, and partial of that with respect to y is just going to be 2x. Let's look at the partial of g with respect to x. This is going to be equal to, now here's my g, so that's just going to be 2x. Notice that these are equal. So I'll need to do the partial of f with respect to z, just following along with this little guy right here. And I'll write all this down. Alright, after going through these partials, I find that theorem 15.3 holds for part B, and therefore f is conservative once again. They give us a procedure for finding our potential functions. So we're going to follow their procedure. We have some function f. Ours is in 2 space for our first one here, and we're going to find that phi. So the first thing that they tell me to do is integrate phi x dx, and we integrate it with respect to x, and that would mean we're integrating e to the x cosine y dx. This integral is then going to be e to the x cosine y plus some constant. Alright, so after that The next thing we're going to need to do is we take this phi y and we say that it equals minus e to the x sine y plus some c prime of y, and we also know that g equals minus e to the x sine y, which leads us to note that c prime of y is going to equal 0. Therefore, c sub y is any real number. We can choose that to be 0 or whatever, but phi of x y is then equal to e to the x cosine y, and I'm just going to say this c sub y is 0. Alright, for this next part, I see that phi sub x is 2xy minus c squared. Phi sub y is x squared plus 2z, and phi sub z is 2y minus 2xz. For our integral, phi is going to be equal to the integral of this 2xy minus z squared. I'm going to integrate this with respect to x, and you are going to end up with x squared y minus xz squared plus some arbitrary constant that is in terms of y and z. Since our phi now is just we did this with respect to x, we're going to get phi sub y equal to, and I'm going to take the derivative of this with respect to my y, so the derivative of this is just going to be 2x, it's just going to be x squared. I'm taking it with respect to y, so that's just going to then be x squared. That is going to be 0 there, so that goes away, and then I have this constant, that this cy that's in terms of y and z. Alright, so what we're doing now is we're just trying to get this guy right here. I note that g is equal to x squared plus 2z. This means that cy z will then be equal to 2z, and to obtain this just plain old c, I'm going to integrate this with respect to y holding z fixed, so that is going to give me c y z equals 2yz plus some function of z. So now I just got to get that d sub z. In order to determine d sub z, I'm going to differentiate phi with respect to z. So I'm going to differentiate this guy with respect to z. Doing that, phi sub z is then going to be equal to minus 2xz plus 2y plus d prime of z. Alright, almost there. I know that h equals 2y minus 2xz, so therefore d prime of z equals z, or in other words, d of z is some real number which we're going to make to be 0. This ends up with phi being equal to x squared y minus 2xz squared plus 2yz, because I let that dz be 0. In this next example, I am going to have to find these line integrals, just like we were doing in the previous section. So I'm going to do this for C1 and also for C2. So for C1, I need to find r prime of t, and this is going to be taking that derivative of my r, that is just minus sine t, cosine t, and my f function would then be equal to, for this one, f vector actually, is then going to be equal to cosine t, because f is x and then the minus y, so that's just going to be cosine t and then minus sine t, just using these points and this here. Next I need to do my integral. So this is going to be integral from 0 to pi over 2. I'm going to take the dot product of both my f and my r prime of t, so those are two vectors, cosine t minus sine t, dot product with minus sine t, cosine t, dt. Doing that dot product, you will then get, when you do the algebra of this, minus sine 2t using your double angle formulas to make it easy to integrate, and you will get that this equals -1 for your first curve. For your second curve, I have that r prime of t. It's going to be -1, 1. Note right here, there's my r for this second one. That means that my f vector is going to be equal to the 1 minus t and -t. Right, I'll do that integral, and that will be from 0 to 1 using my f vector dot product with my r prime with respect to t. You will then get integral of 0, 1 of -1 dt, and that equals -1, meaning that they are the same. Next I'm going to use our theorem to say phi sub b minus, oops, that's supposed to be a phi. Alright, using my theorem, I get that this also equals -1. For our next example 4, or to compute this integral, well, we can use our theorem to state that this integral is the gradient of x squared y minus x z squared plus 2yz dot dr, because this happens to be my phi. That means that I have phi of 1, 2, 3 minus phi of -3 minus 2 minus 1, and that computation will yield 16. Okay, just getting some of the pieces and parts here. I went ahead and got the gradient of f by taking my partials and found the derivative of r. Next I'm going to find this integral. I'm going to substitute here for f minus y plus z, and this is minus x plus z, x plus y, dot product my dr. This is going to end up with 0 to 2 pi sine of 2t dt, and for this you will end up with minus 1/2 cosine 2t evaluated from 2 pi to 0 will get you 0. So this line integral of this conservative vector field on a closed curve C is 0. And that concludes section 15.3. If you have questions, please send me an email or see me at the Collaborate.